So let's get started. Welcome everybody to the fall 2025 edition of the SNAPP seminar. We're delighted that you're here to join us, and we're delighted to have Bora Keskin as our sort of first speaker. So Bora is an associate professor of operations management at the Fuqua School of Business at Duke University. His work is largely on decision-making under uncertainty on a range of applications, from supply chains to blockchains and other non-chain things in between. He's the winner of the Lanchester Prize and recently the MSOM Young Scholar Prize. And today he's going to tell us about a sort of data-driven scheduling problem in healthcare. So please, Bora, take it away.
Thank you, Zil, for the great introduction. I greatly appreciate it. And thank you so much for joining to this seminar. It's a great pleasure to share my research with a distinguished audience and at the intersection of such important fields. As Zil mentioned, I'm going to talk about feature-based scheduling and dynamic learning with a large backlog in this talk. First, let me provide a little bit a brief overview of my research so that you see where I'm coming from. I'm very passionate about data-driven decision-making problems, especially in complex business environments. And naturally, in these kind of environments, there's a fundamental learning versus earning trade-off. What is that? Usually, whenever you are collecting data, you need to think about, should I focus on experimentation, learning to increase my future rewards, or just focus on short-term, immediate rewards? That's the typical fundamental trade-off between learning and earning, and I'm really passionate about that, and I've had the opportunity to work on that in different contexts. And one thing I'm really passionate about in particular is building models and methods based on real-life data. There's an element of that in many of my papers. One particular application is the one I'm going to talk about today. We have a real-life data set from Duke University Hospital and a very fruitful collaboration. And I'm going to talk about this in detail. But it's not limited to that. I'm also very excited about another collaboration with our local airport here. So I'm at Duke University, and we have this collaboration at the Raleigh-Durham Airport. And we have installed sensors in one of the terminals here. We count passengers coming in and going out of the TSA area, and it actually helps us keep track of the passenger populations or service populations in a very interesting real-life environment. And this led to multiple research papers. On top of these, I've also had the opportunity to collaborate with online travel platforms about how sellers on these platforms select their images to maximize conversion. And this research led to a field experiment confirming that the method we propose, which I'm not going to talk about today, but one method that is based on deep learning can actually increase revenues by millions of dollars, about $2 million a year. And in another project, we had the opportunity to collaborate with a large supermarket chain. Again, we use a real-life data set to look at the interplay between perishability and learning and earning. So these are some examples of building models and methods based on real-life data that I'm really passionate about. During my PhD days, I've had the opportunity to work on myopic decision rules and incomplete learning because whenever you look at a real-life data set, usually you would see some sort of short-term focus. When you have large data set, learning should take care of itself. So that's the common notion we see in practice. And I actually had the opportunity to analyze these kind of short-term myopic decision rules in data-driven settings and how they can suffer from incomplete learning. And to complement those results, I also worked on deriving general sufficient conditions for asymptotic optimality in those learning contexts. More recently, I started working on non-stationary or changing demand environments and how they affect the interplay between learning and earning. High dimensionality is another big issue here. So big data and high dimensionality, how does it affect the trade-off between learning and earning? And more recently, behavioral effects like reference price effects and also strategic customer behavior. How do these affect the trade-off between learning and earning? I'm going to touch upon the strategic customer behavior when I review the literature, but this is just a very broad overview of where I'm coming from. So this is my main research. More recently, I had the opportunity to analyze design and management of online platforms, which is a very important topic, rapidly expanding literature. My research includes competition between platforms and multi-homing of service providers in this context, information disclosure and pricing incentives on platforms, which is also related to the first point I mentioned, sustainability issues, for example, introducing green vehicles to platforms, and order stacking, like pooling in the context of delivery platforms. So these are some of the recent research I have been working on. And a separate third topic is, as Ziv mentioned in the beginning, I also had the opportunity to work on supply chains, specifically information and technology management. For example, end-to-end transparency enabled by blockchain technology. What's the value of that? And what are the complications that might arise? I worked on this in a recent paper called Blockchain News Vendor. And another topic I worked on is information asymmetry in supply chain disruptions. So this is just a very broad overview of my research. If you have any questions about the side topics, I'd be happy to discuss those offline. So let me just go to our main focus today, specifically feature-based scheduling with a large backlog. And the main motivation for this research is the COVID-19 pandemic. Most of you are probably aware, the pandemic created a huge backlog for surgeries. And this is everywhere, not just at Duke University Hospital. And this has been documented by Harvard Business Review, consulting companies like McKinsey, as well as some medical journals. So there are also this Lancet, they also have this documentation of the surgery backlog. And the keyword is backlog here. So you can see in all of the titles. And this was also the case for Duke University Hospital. Around the time of the pandemic, they sent out an email stating that they are forming a task force to clear the backlog. And also they invited collaborations. And we said, okay, we are operations people. We know about scheduling and maybe clearing backlogs. So we joined in, and it was a very interesting collaboration for us. At the time when I first started these discussions with the surgeons at Duke University, my main idea was just to help. So I was just trying to think of perhaps coming up with useful suggestions, maybe quick and dirty solutions, off-the-shelf methods that might actually be valuable for them, because they were trying to use data to come up with a good solution to this problem. And my first thought was just offer something off the shelf and maybe help them. But over time, we realized that this is actually a deeper problem, and it can actually lead to some theoretical contributions. But I'm going to talk about that in a moment. So let me show you the size of the backlog. In that year, 2020, we've seen a huge decrease in elective surgeries. And just to clarify, I'm not talking about all the surgeries here. So emergency surgeries that are very urgent, they were actually performed at a limited volume. But if there were elective surgeries that could be delayed, these surgeries were delayed to a later date. And we've seen a significant delay around March, April, May of 2020, and continuing on to the rest of the year. So there was a very decreased volume. This created a huge backlog for the surgeries. And this is around May, we actually started collaborating with the surgeons at the Duke University Hospital, and main focus was the patient prioritization to clear the elective surgery backlog. And we've had lots of discussions. Essentially, we were meeting every week. There was a task force, and we had very fruitful discussions. And this allowed us to identify several types of constraints in the system. It's a very complex problem. The model I'm going to discuss is a stylized representation of reality. The problem is actually very complex. There are many different types of resources, and all of them are constrained. For example, operating room is a resource constraint. Surgeons' capacity, you can think of this as surgeon hours. It's limited. ICU capacity. That's also limited. And based on our discussions with the surgeons, we realized that the intensive care unit or ICU bed capacity was the most critical resource. This was the most constrained resource. So we wanted to focus on that in this project. And one important challenge in this context is that when you focus on the ICU, the discharge rules change after the pandemic, and borderline cases were handled differently. Some of the patients who had COVID were directed to a separate ICU, and there was a non-COVID ICU. When you separate populations like that, the amount of time, the expected amount of time they are going to spend in the ICU is going to change. So there was lots of uncertainty about how this critical resource was going to be used. So that actually shaped our main problem. So it's crucial for the hospital to leverage the most recent information to learn patients' expected length of stay in the ICU. So that was our main learning problem. And just to take a step back, when you think about these kind of problems, feature-based scheduling and dynamic learning with a large backlog, apart from the pandemic and surgeries, you can also think about mass casualty events, for example, earthquakes. This could give you another reason, another motivation for large backlogs of patients in need of critical medical services. And because these are really rare events, you would have limited information to estimate the expected service times of individual patients. And this is another setting in which where you will have large backlog and you need to do some data-driven learning. So this is the motivation of our study. As with any Zoom talk, I'm going to pause for a few seconds to see if there are any questions. If there are any questions, I think it's a good time to ask. Any questions about motivation? I'm going to pause. We are going to enjoy the silence for 10 seconds. Right, I'm going to assume everything is clear so far about the motivation. Before I dig deeper into the details, I would like to give a high-level overview of main contributions of this work. So what are we doing here? So let me just do that. To our knowledge, this is the first study to analyze data-driven feature-based scheduling for backlog clearance. So this is a new problem to our knowledge. And there are some novel features that make the problem especially interesting, and I'm going to list them here. We are going to be discussing them in more detail in a moment, but let me just list them. Each job can only be served once, and this is different from finite arm banded problems. Of course, there could be other type of problems this could be related to, but when I first started this project, as I said earlier, my main objective was to help, and I tried to suggest some of the readily available off-the-shelf bandit algorithms that might be useful for our surgeons at Duke University Hospital. But quickly we realized that this is not exactly a bandit setting, because in a bandit problem, you might have a large number of arms, but when you pull an arm, you can actually pull the same arm again. So here, each job can only be served once. The patient comes in, and you perform the surgery, and they leave. And you can't really perform the same surgery on the same patient again. So each job is served only once. And the second difference is suboptimal decisions have lasting impacts on the remaining jobs, and they can cause delays. They can delay every subsequent job. And that's also another difference. Again, comparing with the bandit problems, finite arm bandit problems, when you make a decision, usually you have a reward that's well-defined for a single period, and then you move on to the next period, and that gives you another decision opportunity. And the interaction between them is just the information you have. So here, suboptimal decisions have lasting impact, and they can cause delays for all remaining jobs. And finally, we can also try to compare this to learning problems in queuing context, but this is not exactly a queuing problem because all jobs are available at the beginning. So we are focusing on a backlog. So the backlog is there in period 0 before the problem starts, and they're all available. And these features are quite important, and together, these 3 features make the problem different from the other problems that we are aware of. And we actually have some new results for the setting. So what are the bad news? Characterizing problem complexities, the worst case loss in our problem is super linear in problem scale. I'm going to use some diagrams to illustrate this, but let me just first mention this. In learning problems, typically we are interested in loss, and that's usually measured in terms of regret. I'm going to describe it in a moment. And in this context, we show that in our problem, the worst case loss is super linear in problem scale, which is quite interesting because typically in learning problems, you have sublinear loss in terms of problem scale. So when you increase the problem, it becomes easier and easier. So we have more and more efficient algorithms. So that's what we are observing here. And on the positive side, we developed some near optimal policies, specifically two policies, learn and commit for backlog clearance and uncertainty ellipsoid policy for backlog clearance. I'm going to define those policies, and they perform near optimally in this context. And finally, we have a case study based on real life data coming from Duke University Hospital, and this is elective surgery data. It's a very large data set we have been working on, and that's also part of our study. And if time allows, I'll also dig deeper into that. Any questions about the main contributions? All right. It seems no questions. I'm not going to discuss specific papers in terms of the related literature. I already shared the paper before the talk, so for details, please check the literature review, but I'm going to give a large overview. I think this is more helpful for the seminar and for the talk. So when you think about dynamic learning problems at a very high level, we have an unknown theta. So this could be a scalar, it could be a vector, it could be a function, it could be quite complex, but in all kinds of learning problems, there's some unknown theta, and there's some problem scale, and that's typically the number of decision opportunities you have in the problem. For dynamic pricing problems, it could be the pricing opportunities, or it could be the number of customers. For healthcare problem, it's the number of patients, but in all of these learning problems, you have problem scale n. And the performance metric for learning is typically regret, and this can be described as the cumulative loss due to not knowing theta. So if you knew theta, you would have zero regret, so you would always choose the full information optimal decisions, but because you don't know theta, you would have some regret, and you would just use this performance metric. And typically, you would have bunch of different results. There's a huge literature on regret, computer science, in statistics, in operations research, in operations management. Usually you would get a regret result between order 1 up to order n. Order 1 means that regret is bounded by a constant independent of problem scale. Order n means that regret is linear in the problem scale, which is very, very bad. And in this green region, up to order square root n regret, you actually have very well-performing policies. In this orange region to the right, regret is typically high, close to linear regret. It could be order n to the 2/3. For example, there is a branch of the literature that looks at the value of offline data, and you can actually show that if you have some offline data set that exhibits enough variation, you can reduce your regret to order log n. So that's good. You can actually move closer to order 1 regret. If you have changing environment, in the case of abrupt changes, big changes throughout the time horizon, you can use change point detection, and you can have order square root and regret. Or in the case of smooth gradual changes, an accumulation of smooth gradual changes, you cannot use change point detection, and you would have to incur at least order n to the 2/3 regret. So you are in the orange region. And more recently, people looked at Markov modulated changes. When you have an exogenous Markov modulated change in your learning problem, again, you can usually get order square root n regret. And in recent years, researchers have expanded this literature to multi-agent learning problems. If you have strategic agents with rational expectations, typically you have results in the green region. Whereas if you have learning agents with imperfect predictions, you would typically have results in the orange region. And this might be at first counterintuitive, but it makes sense from a learning perspective. In a full information setting, when there's no learning, typically strategic agents are more difficult to deal with because they can actually have precise predictions. But from a learning standpoint, they're very easy to predict. So you can actually use their rational expectations to learn about them faster. Whereas imperfect predictions could be anything. It could be a really worst case scenario. So they can actually lead to higher regret. This is a very, very high level overview of the literature on learning and earning and dynamic learning problems. Now, what are we doing? How do I position this work I'm presenting today on this scale? We are actually getting a new set of results to the right of the scale. So we are essentially breaking the scale on the right-hand side. And this work shows that clearing backlogs is actually a fundamentally difficult problem with an order of magnitude higher regret. And specifically, we are going to show that the regret here is going to be in the order of n to the 3 halves. And we have lower and upper bounds on this. So this is quite precise. I'm going to talk about the lower and upper bounds, but that's how we position it in the literature. Any questions about this, about the literature?
I have a question about the abrupt versus smooth changes. Is there, and if the answer is go read the literature, that's fine. Is there an intuition for why abrupt changes are easier than smooth changes?
Wonderful question. So if you are actually measuring a cumulative amount of change throughout an entire time horizon, and then thinking about abrupt versus smooth changes, abrupt changes are easier for learning because you can use change point detection.
Because you know when they happen, whereas the smooth change sneaks up on you.
Right, and smooth changes, you cannot really use change point detection, and the best you can do is some filtering. So you basically filter out all the data without really detecting any specific change. But that's a very good question. Thank you, Zed, for this question.
Okay, thanks.
Any other question about the literature? And I love talking about the literature, and any other questions, I would be happy to take them offline. You can always email me after the talk. I would be happy to talk about them. So let's talk about the model. So let's consider a server and the backlog of n jobs. And service times of these jobs depend on patient features. So job and patient I'm going to use interchangeably because of the motivation I mentioned earlier. And all of these features are potentially important in terms of the service time, so they can influence the service time. What do they include? Age, gender, surgery division, CPT code, which essentially describes the type of procedure the patient is having. And there are also a bunch of other features. We have very rich data set with lots of features, even some health indicators for the individual patients. So let's summarize all of that in a feature vector, ZI. And it's a d-dimensional vector in the Euclidean d-dimensional Euclidean space. And for reasons that will become apparent in a moment, I'm going to add a 1 to the beginning of this vector. So I'm going to call this the augmented feature vector xi, which is bounded. It has a bounded norm. And I'm going to use a feature vector and augmented feature interchangeably from this moment onward, because the only difference is that there's a 1 at the beginning of the augmented feature vector. And the service times come from this equation in the blue rectangle. So service time yi, the service time of patient I, is going to be theta transpose xi plus epsilon I. So theta is this unknown vector which comes from a compact set. And the epsilon i's are independent zero mean sub-Gaussian random variables. So these are essentially the noise terms. And the service times are going to be generated from this model. The decision maker knows xi, so it knows all the features that are in the backlog, and this decision maker does not know theta. So that's the essential learning problem. And there's also a weighting cost associated with each patient. This can actually incorporate how critical the patient is. So delay is going to be more costly for certain patients, and we allow for differentiation here. If your problem in this context have no differentiation, you can actually have the CI of 1 for all patients. In that case, we are just going to think about the shortest processing time. Admissible policies in this context are decisions that basically decide on which job to serve next after each job is served. And at any given point in time, these policies have the entire history available at their disposal. And this history includes all the jobs that are selected in the previous periods, so in the previous decision opportunities from 1 to n-1, and also their realized service times, so y1 through yn-1. And the admissible decision rule here in this context is a function that maps the history available at that point to one of the remaining jobs. And when you form a sequence of these decision rules, you have an admissible policy, which I denote by the Greek letter pi. And the objective is to minimize total waiting cost of all patients. It's actually a weighted waiting cost because we have the CIs as well. So we actually use some weights. And if you had full information, if you already know theta, you would use a clairvoyant policy. And this is already well known in the literature. It's very well studied. And we know this as the CMU rule. So it will prioritize a job with the lowest expected waiting time divided by the cost. So here in this context, the expected waiting time is theta transpose xi, and it's going to be divided by ci. And when theta is known, we know this is optimal. Actually, there's a very easy proof to show that in dynamic programming books. There's the scheduling and the interchange argument, and you can actually easily show that this is optimal when theta is known. And the intuition is that you want to process the job with the shortest processing time first. And at the same time, you want to choose the jobs with the higher waiting cost. So that's why you are just going to choose the lowest theta transpose x divided by ci. Is that clear to everybody? All right. Now, what's our performance metric? Given that we have a learning problem, we have a theta and the backlog xn features, all of the features and the patients in the backlog. And we define the waiting time of job I under a given policy pi. And that's going to be shown as W superscript pi. And when you have W superscript star, that's going to be the waiting time of job I under the clairvoyant policy. And using those definitions, we can define expected regret. So this is based on the CMU objective. So we want to minimize this expected regret given the backlog we have. And the worst case expected regret is basically we take a supermum over all possible thetas in the compact set capital theta. And we also think about all the possible feature vectors in a set of feasible feature vectors. And that's going to be our worst case regret. So R superscript of n is the worst case expected regret in our problem when the policy being exercised is pi and the number of decision opportunities is n. So n is the problem scale. Right. I'm going to pause for a couple of seconds, see if there are any questions so far.
Could I maybe ask one question?
Yes.
So you're using CMU policy as a benchmark. Is it like optimal, or is it like near optimal as n goes to infinity in this context? Because in general queuing context, generally you show mostly that it is like some kind of asymptotic optimality of such policies.
That's a very good question. As a matter of fact, in the full information version of this problem, in the clairvoyant problem, we know that the CMU rule is exactly optimal.
I see. Okay.
Exactly optimal. But you have a very important point. So we are actually working on an extension, which I'm not going to talk about today, but now I have the opportunity to talk about it since you asked the question. So we are actually looking at this extension where the C's can deteriorate over time, which means that the CMU rule is not exactly optimal. But there are actually some existing results in the literature that show that CMU rule is asymptotically optimal, and we actually show that by using a bridging problem and using the benchmark of the CMU, we can still get a near optimal regret. But it actually it's a more involved proof because there are two steps. First, you use a CMU benchmark, which you know is not exactly optimal, and then you show that not so optimal benchmark is close to the exactly optimal benchmark.
Right, right. So maybe one more question, like what is the motivation of having these CIs in this context?
Oh, that's a very good question. So this is based on our conversations with the surgeons. So not all patients were the same in this context. So some of them were prioritized. It's just about having two elective surgeries. And I'm just going to give some example. On one hand, you might have an ear, nose, throat surgery. On the other hand, you might have a brain surgery. And surgeons want to give a higher weight to the brain surgery. And this allows this flexibility. But if you don't like that, you can just give the weight of one.
Right. No, I guess my question was coming from because you mentioned elective surgeries, and so I imagine them to be not like life-threatening or something.
Right.
So
Correct. That's correct. So it's basically a nuance here. So you can still fine-tune it. Even between elective surgeries, there are certain ones you want to prioritize, and this gives the decision makers, in this case surgeons, some flexibility. But that's a very good question.
and then what's the motivation for the extension that the CIs are deteriorating over time?
Oh, that's also a very good question. So this is something we received in our reviews, sometimes the outcome of the surgery may deteriorate significantly if you delay the surgery. So the CI is not going to be constant over time, but increasing with T, which greatly complicates the optimization problem because you don't really have the exactly optimal policy. But in large scales, you know that CMU rule is essentially optimal in this context, and you can still solve it.
Okay, thanks. Thank you.
Thank you for the great questions. Any other questions? All right. In the interest of time, I'm just going to move on. So I'm just going to reiterate some of the key challenges and novel aspects. I already mentioned some of these at the beginning, but now they're going to be a bit more meaningful. So unlike arms and banded problems, each job can only be selected once. A suboptimal decision in one period has a lasting effect and causes delays for all remaining jobs. And unlike in queuing system with sequential arrivals, all jobs are available at the beginning. And this last point makes the clairvoyant policy much stronger. So the clairvoyant policy can actually determine the entire sequence of all jobs throughout the entire time horizon. In queuing problems, even the clairvoyant policy cannot do that. So we have a stronger clairvoyant policy in this regard. And this will affect the bounds. Now, let me move on to our first result, characterizing problem complexity. We actually showed that the worst case regret for the problem scale n is at least in the order of n to the 3/2. So this is a lower bound, and it applies to any given policy. Fine. So for all policies, this has to be true. And this essentially shows that the worst case regret is superlinear in problem scale in this context. Now, what are the managerial implications? Best achievable regret is superlinear in the backlog size. This means that the decision maker has to be especially careful in this problem because any mistake is very costly compared to other learning problems. And finally, it actually provides a sharp contrast for scheduling problems in queuing systems with sequential arrivals, because there are actually some papers in the literature that look at dynamic arrivals, sequential arrivals in this context. And you can actually show that an order log n regret is valid in those settings. But we are essentially showing that when you remove the dynamic arrivals and have a backlog instead, you actually have super linear regret. So the complexity of the problem significantly changes. So that's one finding we have based on this result. Now, we have time for a proof sketch. So I'm just going to provide a little proof sketch. And of course, I'd be happy to talk about this offline, but I want to give the general idea of deriving this proof. So challenge number one here is that suboptimal decisions have lasting effects and cause delays for all remaining jobs. And that's why we need to have a regret decomposition. And we are going to define these lowercase r terms that define the regret of a policy in period n and following the clairvoyant policy or full information optimal policy in the future periods. So when you define that, we are actually able to decompose regret. Otherwise, decomposition is difficult because every decision has a lasting impact. But with this definition, we can decompose regret. And once the decomposition is done, we move on to the second challenge. Unlike arms in bandit problems, each job can only be selected once in our setting. And in the bandit literature, there are some really cool proof techniques that I really enjoy. So you construct a worst case problem instance where you have a best arm and a subset of second best arms or suboptimal arms. And the nice trick there is you actually design the worst case instance such that the second best arms are clearly suboptimal, but also sufficiently close to the optimal so that learning the best arm is difficult. So you need to take time. You need to exert an effort to figure out which arm is the best arm. So usually you have a delta gap between the best arm and the second best arm. So this delta gap proof technique is really cool and it works in many different problems, but it's no longer applicable in the setting because once you pull an arm in this problem, it just disappears. So you need to think about a bunch of arms and they need to be pulled. And so the same proof technique is not directly applicable in this context. So what do? We partition jobs to 2D types, N over D jobs of each type. And then we have these patient features. We put a 1 to a specific component of the feature vector and zeros to all other components. And when we design the unknown theta, components of the unknown theta, we actually think about different degrees of difficulty. So instead of having this fixed delta gap argument, we have varying degrees of difficulty in figuring out the exact value of theta. So we have plus or minus delta, we have plus or minus delta over D, and everything in between. And the value of the delta should be selected specifically so that it's a challenging learning problem. Once you own that, it's possible to show that in the first half of the time horizon, N over 2 jobs, you will make mistakes with some positive probability. And each of these mistakes are going to delay the second half of jobs significantly. So N mistakes, each mistake is costing something in the order of N because it's going to delay everything after itself. And these mistakes are going to be in the size of delta, and delta is in the order of 1 over square root N. So N times N divided by 1 over square root N, it gives you N to the 3 halves. So that's basically the proof sketch. This is very high level. Of course, the actual proof has lots of details, but I just wanted to give you the high level argument. Now, how do we get good performance in this setting? We design some near optimal policies, learn then commit for backlog clearance, or LCBC in short. It's a very simple policy, and it works under this assumption. Given the backlog of feature variables, you will assume that there is a subset that has sufficient variation. The minimum eigenvalue of the subset is at least in the order of the cardinality of the subset. If you don't have any subset like that, there's no way to learn. We actually justify this assumption with a lemma, a plausibility lemma in the paper. But once you have this assumption, you can use the LCBC policy and randomly choose one of the remaining jobs in this subset I mentioned. And then at any given period, you compute the least squares estimate for the unknown theta, and then choose the remaining job with the lowest theta transpose xi divided by ci. Essentially the CMU rule by plugging in the estimate of the theta hat into theta. And if you use this policy, the regret is at most in the order of n to the 5/3. As you might realize, this is not exactly 3 halves, so it's actually higher than that. This is actually the price of using such a simple policy here. It's still close. It's not n squared, but it's not n to the 3 halves either. So this is the performance guarantee we provide for the LCBC policy. And if you don't like this upper bound, or if you don't like assumption 1, we have a more general result using the uncertainty ellipsoid approach. So this approach is a bit more complex, but it has its roots in the bandit literature, going back to upper confidence bound policies. So at any given point in time in a bandit problem, you might want to choose an optimistic option to encourage experimentation. That's the upper confidence bound idea coming from the bandit literature, and it has been applied to continuum arm bandits in the form of an uncertainty ellipsoid. The high-level idea is basically constructing a high-dimensional ellipsoid in the parameter space, unknown parameter space theta. And then this ellipsoid is going to measure the amount of information you have in each dimension. If you have a high radii in one dimension, it means that you have a lot of uncertainty in that direction. If you have a very small radius, then you are going to have almost certainty in that direction. And by just repeating this process, you will update your ellipsoid and choose optimistic options within that ellipsoid. And this is what this policy does. At any given point in time, it just builds this uncertainty ellipsoid, Cn-1, and within that ellipsoid, it just chooses the most optimistic, like the lowest cost option within the ellipsoid. And if you use this policy, uncertainty ellipsoid policy, without assumption 1, you get an upper bound of n to the 3 halves, which is height in this case. All right, these are the theoretical results. I'm going to pause for questions. Any questions so far?
Okay, I have a question. So I'm not super familiar with the sort of linear bandit literature. Is the way I can think about if I were to sort of specialize this construction to something that looked more like traditional bandits, would I basically kind of get UCB? And so I can think of this as a sort of multidimensional generalization of UCB.
Yeah. So first of all, we are not the ones who came up with the uncertainty ellipsoid idea. So it's already applied to linear contextual bandits. And you are right. The intuition is similar. So the key idea comes from older days, from the upper confidence bounds. And then this was extended to linear contextual bandits. The key idea is basically choosing an optimistic choice, optimistic option, optimistic decision, given your uncertainty. And this naturally encourages experimentation, because when you choose the optimistic approaches, for example, in the finite unbanded problem, if you are very uncertain about one arm, the upper confidence bound is going to be really high. So you basically choose that one. It encourages experimentation. The same idea is applicable to linear contextual bandits, and the optimistic choice is going to encourage optimization. You'll choose something perhaps towards the high radius of the high dimensional ellipsoid. So the key idea, I think, is very similar.
Cool. And then about the sort of, so you sketch this lower bound proof where it's like, you're guaranteed to make this many mistakes here, or you have a constant probability of these mistakes in the first half, which will give you this damage to the second half. Right. Does the regret upper bound follow similar structure? Or I guess you might need to do more because you need to think not just about the halves.
That's a good point. So some of the intuition also needs to apply there too. When you decompose regret, you need to think of in similar terms. So that part is valuable for both upper bound derivation and lower bound derivation. So that's a very good question.
Thanks.
Thank you, Zev, for the great questions. Any other question?
Oh, sorry, I have a question.
Yeah.
Actually, in linear bandit literature, there is an interest in deriving gap-dependent bounds, which are not kind of worst case. I was wondering if here we can define the dependency on the smallest gap or something similar.
Another good question. Thank you for this question. So you are right. So in bandit problems, you usually have typical two types of bounds. One is gap dependent, that depends on the delta I mentioned, and another one that doesn't depend on delta. And this basically boils down to whether the decision maker knows whether there's such a gap or not. If the decision maker knows whether there's such a gap, then you'll have the gap dependent bounds apply. If the decision maker does not know that, you'll have gap independent bounds or instance independent bounds. The bounds you are seeing in this talk, they are all instance independent, so they don't really depend on the gap. We are actually picking the worst case gap in that regard. it is possible to do. One can write another paper with gap-dependent bounds in this context. I think that would be interesting, and we can actually get different types of results. But all the results I've shown so far, they are for the gap-independent version of this problem. Because again, going to our motivation, the decision makers, they didn't really know anything about this context, so we didn't really want to make that assumption that they know the gap.
Okay, thank you.
Okay. Any other questions? If not, I'm going to move on. I want to leave some time at the end for questions. So these are the theoretical results. I'm done with them. So now I'm going to show some simulation experiments. Hopefully, they will give some further insights and the real-life data-driven case study. So let's think about an experimental setup with two types of patients. Their feature vectors are 1, 1, and 1, 0. And the true parameter vector is theta, which is equal to 3 and 1. And immediately you can see here is that the second type of patients that has a 0 in their vector is better because they have shorter expected waiting time. So I'm essentially thinking about theta transpose x as the expected service time or expected processing time. And if I think about these two patients, the first one that doesn't have a 0 is type 1. The one that has a 0 is type 0. It's optimal to prioritize all type 0 patients because waiting costs are all 1. So here, in the setting, waiting costs are all 1. So I need to prioritize type 0 patients, and then I should schedule type 1 patients. It's a very simple, very stylized example. And in this context, we have the noise terms that provide sufficient variation. They are IID and binary valued, plus or minus 2 with equal probabilities. And in this context, if you use LCBC, UEBC that are defined, they perform quite well. The bottom curve is UEBC, that's the best one. LCBC is a bit worse, but still better than a myopic policy, which is a top curve in this graph. The myopic policy in this context actually has order n squared regret because it can actually schedule the wrong type of job for the first half of the time horizon, and then it will delay everything significantly. Let me illustrate that. So it's the same problem. If you look at the myopic policy, and in this graph, I'm showing in the horizontal axis the periods, and the vertical axis the cumulative number of type 0 patients treated. As I discussed in the previous slide, the optimal thing to do is to schedule all the type 0 patients first and all the type 1 patients later. But as you can see in these sample paths, sometimes, actually half of the time, the myopic policy is scheduling type 1 patients first, because as soon as you get the wrong sign of theta, it will just keep scheduling the wrong type of patients until the middle of the time horizon, and this will delay everything. So that's why the myopic policy has order n squared regret. Whereas LCBC doesn't make that mistake, so it doesn't get stuck like that. And similarly, UEBC doesn't really schedule any type 1 patients in the beginning, or a substantial number of type 1 patients at the beginning. So that's why these policies are better in the simulation experiment. Now, in the limited time, I'm just going to quickly go over the case study on real-life data. We have, as I mentioned earlier, an elective surgery data set from Duke University Hospital. The date ranges from August 2020 to February 2021. We have lots of patient features: age, gender, surgery division, the CPT code, which basically describes the surgery, and an ASA score that describes the situation, the health status of the patient. We have the realized ICU length of stay or service times for each patient. And we also went over all types of surgeries with our expert team, the surgeons at Duke University Hospital, and they actually assigned a waiting cost to each surgery type on a scale of 1 to 10 per day. We have all that data, and we used two approaches. First, we calibrated our model. So we used our model, we calibrated its parameters and simulated the expected regret of different policies. And the nice part about this is this allows us to generate multiple sample paths, so we can actually look at the expected regret. And we also have a model-free approach. So we didn't use our model for the second approach. We just used realized ICU length of stay, and we used the policies that I just described, and we computed the regret for different policies. So the nice part of this approach is it's model-free, so it doesn't depend on our model in any way. So we just use the realized ICU length of stay. Now let me first show the results of the calibration study. If you use the LCBC or UEBC in this context, they're both pretty good. And we learned that in practice, a very commonly used policy is a C-only policy. They don't really look at the expected waiting times, but just you look at the C part of the C-mu rule. And if you use that, you have more regret. But one important observation is that the LCBC and UEBC, they are close to each other. So even though their theoretical performance guarantees are not exactly the same, the simple learn and commit policy is pretty good in practice. So that's one observation here. When we look at the model-free analysis, as I said, we have the advantage of not relying on our model in this context, and the uncertainty ellipsoid and learn and commit policies are performing really well. And they actually cut the regret almost by half compared to the C-only policy and also the current practice. We can actually make a comparison with the current practice here because that's a model-free approach. We just look at the historical data. And current practice is actually very close to the C-only policy. That's not surprising because we already heard from our surgeon collaborators that they're using something similar to C-only in practice. So this is not surprising. But the learning policies can actually cut the regret by half. In the interest of time, do I have more time or should we start the questions? What do you think, sir?
I think it's best if you can maybe wrap up in the next sort of 3-ish minutes.
Okay.
And we can take a few minutes for questions at the end.
Okay, I'll do that real quick. So I'm just going to display the slide. We also did an extension. I'm not going to go into the details, but what if you had an initial warm-up data? So what if you wanted to use some of the data set that was generated in like even pre-COVID times? Would it really help? It does actually help. And the lower bound stays the same. The bound for the uncertainty ellipsoid policy stays the same. But if the data set is sufficiently large, you can actually bring down its regret back to the lower bound. So that's one technical result we derived in this context. And we also extended our results to high dimensionality. So if you have a large feature vector and most of them have zero impact on service times, then you can actually investigate how the bounds depend on dimensionality. And we actually were able to generate a square root S term, both in the lower bound and the upper bound. So it seems like there's a square root S dependence in terms of the number of true predictors in this context. So that's something we derived. And I'm just going to display the main contributions again. So, and I also wanted to add the extensions here. Because I need to wrap up in 1 minute, I'm just going to go back to the literature and mention 2 more studies that I recently worked on. So this was the literature slide that I mentioned earlier. So as I mentioned, our paper breaks the scale on the right-hand side and shows that clearing backlogs is a fundamentally more complex problem. As a matter of fact, tracking service populations in the other context I mentioned, in the airport context, is also a fundamental problem. When you look at the cumulative loss in that setting, you also get super linear cumulative loss. I'm not going to talk about that today, but if you're interested, please contact me and I'll be happy to share the paper. So this is another problem where the regret scale can be distorted. And I want to mention that there are also lots of future research opportunities in multi-agent learning, especially in that context. If you have multi-agent learning with many sellers, one benchmark that's typically used is the full information Nash equilibrium. And in one paper, we were able to show that one can achieve something better than that. This is quote unquote negative regret, meaning that you achieve something better than the full information Nash equilibrium. And there are many other opportunities about multi-agent learning problems. This is the end of my talk. I have a few more minutes to answer questions. I'd be happy to answer your questions. Thanks for coming.
All right, let's give Bora a virtual hand. Thanks for a great talk, Bora. So
Thank
we have a few minutes for questions. So any questions from the audience? I still have some more questions, but first let's open.
Maybe just a quick question. In the offline data case, I'm just trying to understand, like if you have a lot of offline data, the lower bound should also go to 0, I would imagine, right? If you have infinite offline data, then you just know theta, it's the same thing as knowing theta.
That's a good question. In some settings, yes, it might. It can actually go down to order 1 regret, basically, but it's not always the case. It really depends on what kind of offline data you have. So now there's a stream of literature on this. There are multiple papers. One paper I worked on looks at essentially learning 1 point in an unknown curve. So if you, for example, if you think about a dynamic pricing problem where an incumbent price has been charged infinitely many times, and you learn 1 point on that unknown curve. If you know that point exactly, and if you have this infinite prior data set, you can actually have lower and upper bounds on regret that are in the order of log n. And if you have more data, it won't help. But if you have less data, if you don't have infinite data, you can actually have a spectrum of results ranging from order log n up to order square root of n. So if you make the data, prior data, offline data, smaller and smaller, it can go even up to order square root n.
But in your context, seems like the lower bound doesn't change from n to the power 3/2.
So for the initial warm-up data, we considered up to linear
I see.
linear regret. So, and in that case, we are able to bring down only the LCBC upper bound.
Okay, so essentially you need more than the linear amount of data.
You would need a substantial data here. Yeah, that's one thing we realized. And just going back to the practical application, we saw that some of the data is helpful here. So this initial warm-up data could be helpful. And we actually looked at it extensively in the theoretical result. We are actually working on the revision. So this is something came up in the reviews, and we are working on it.
I see. Okay. Thank you.
Thank you for the great questions.
Thank you for the talk. It was quite interesting.
I also have a question.
Please go ahead.
First, thank you for the talk. It was great. And actually, my question is, in bandit literature, the agent who plays randomly will have a linear regret, and by choosing smarter algorithms, you will reduce this to a square root of n. What is the regret of random agent in this problem?
I don't have a theoretical result about that, but I have a very I have a conjecture, which is I think easy to prove. In this context, if you have a myopic policy, it will get an order n squared regret. A randomized policy will also get order n squared regret. The reason is you'll make n mistakes, or in like for a fraction of the jobs, you are going to make mistakes with a randomized policy, and each of these mistakes is going to delay something in the order of n. So it's going to be in the order of n squared. I think that will be a very short proof, which is not in the paper, but I think it will be very straightforward to show that. So randomized policy will have an order n squared regret. Likewise, a myopic policy will have order n squared regret in this problem. And one interesting thing is, if you remove the backlog and add dynamic arrivals to this kind of problem, a myopic policy will have order n regret, order log n regret, which actually brings it down from order n squared down to order log n. So it's really interesting that in a very similar environment, sequential arrivals or backlog, you can get starkly different results.
Is it because the achievable rate is higher when the tasks are sequential?
It's because the clairvoyant in the setting is very strong. So they know the entire sequence of jobs, because it's in the backlog already. And clairvoyant is a very strong benchmark. So that's one of the main reasons, I would say.
Kind of the lower bound is higher when.
Yeah, it basically pushes up everything, and lower bound is higher, and upper bounds also have to be higher in that regard.
Okay, thank you.
Thank you.
I have a question about the sort of the kind of regret scaling. So is this a case where the sorts of instances you're thinking about, how does the optimal policy's cost scale with n? Would it be O of n squared, or I guess omega of n squared?
That's a very good question. So once you have the lower, if you have tight lower and upper bounds, they also apply to the optimal policy, even if it's difficult to compute. Exactly optimal policy in this context is practically impossible to compute because it's a very high dimensional problem and you would need to write a dynamic program and there are at least d dimensions of it. So analyzing it is practically impossible. So there's a theoretical optimal policy, which we cannot directly compute. And if you have tight lower and upper bounds in this context, we do know that the exactly optimal policy should also have order n to the 3/2 regret.
Oh, sure. Sorry. So I'm not talking about. Sorry. Let me. I think when I said optimal, I meant clairvoyant. So the clairvoyant policies, like the regret, is the difference between our cost and clairvoyant cost. And so I know you said, oh yeah, this regret is scaling super linearly, but in a sort of vanilla bandit problem, the rewards all scale linear. The actual rewards scale linearly, and so the sort of benchmark for sort of sublinear regret, like sublinear regret is the natural benchmark, and indeed we get that. What I'm wondering is here, could you basically say, oh, the natural thing to try to achieve is subquadratic regret, and in fact you do achieve that, albeit sort of you achieve, like if you sort of instead of scaling with n, scale as optimal cost, maybe you get optimal cost to the 3/4 is the way to think about it.
Oh, that's a good point. So you don't have a result like that in the paper, but that's a very good question. If I had to guess, I would guess that it will be in the same order. It will be super linear, but yeah, we don't have that result. So maybe we can discuss this offline.
Okay, yeah. Lots of queuing problems will have these sorts of quadratic cost structures, because if you think about, you've got n jobs, every pair of jobs, one needs to wait behind the other. And the exact distributional assumptions will alter whether things scale quadratically or not. So, okay, very interesting.
Okay. Thank you.
All right, any more questions? All right, well, let's thank Bora one more time. And thanks everybody for coming to the first Snap talk of the season. The next talk, there's going to be a bit of a break because we have some holidays, but the next Snap talk will be October 20th. And we'll have Florence Yuchu from Warwick speaking. So see you there.